At sunrise, the storm offshore looks dangerous but familiar. By sunset, the same circulation has built an eye, tightened its wind field, and crossed into an entirely different emergency. The coastline did not move, the forecast clock did. A number that felt stable in the morning can become obsolete before night. Hurricane Otis made that problem impossible to ignore in October 2023. The National Hurricane Center's final report estimates that its maximum wind increased by 90 knots in only 21 hours before Acapulco. That was not a normal strengthening curve. It was a system racing through several states almost at once. But rapid intensification is not magic, and it is not a hurricane discovering a hidden battery at the last second. It happens when several imperfectly observed parts of the ocean, atmosphere, and storm core align. Each part can look merely favorable. Together, they can close a feedback loop that changes the rate of change itself. That distinction matters. A forecast can correctly recognize a favorable environment and still struggle with the exact hour when organization becomes self-sustaining. The question is not only how much energy exists, it is whether the storm can connect that energy to a coherent inner core before shear, dry air, land, or its own mixing interrupts the process. So this is not a story about one warm temperature or one ominous satellite image. We are going to build the intensification system from the water downward and the clouds inward. Then we will see why the same ingredients can produce slow growth in one storm and an explosive transition in another. The payoff is a different way to read intensity forecasts. Not as a single line that claims to know the future, but as a moving probability built from a deep ocean reservoir, an atmospheric window, and a vortex that may or may not lock itself together in time. The operational definition is precise. The National Hurricane Center calls it rapid intensification, when a tropical cyclone's maximum sustained wind increases by at least 30 knots during a 24-hour period. That is about 35 miles per hour added to the strongest sustained wind in one day. The 30-knot line is a classification threshold, not a physical switch. A storm that gains 29 knots has not behaved fundamentally differently from one that gains 31. The threshold gives forecasters and researchers a consistent way to count rare, fast changes and compare the environments in which they occur. It also does not mean the storm jumps exactly one category. Categories are snapshots of maximum wind. Rapid intensification is a rate. A weak tropical storm can begin an RI period without reaching major hurricane strength. A hurricane can cross multiple category boundaries if the increase is large enough and begins near one of those boundaries. What feels sudden to people is the compression of decision time. Forecast advisories arrive on a schedule, while the atmosphere evolves continuously between them. Aircraft, satellite, buoy, radar, and model data may reveal a new structure after preparations have already been based on the previous one. The official forecast then has to catch a moving target. Rapid intensification does not prove that forecasting is useless. Long-term intensity errors have improved, and modern guidance explicitly produces probabilities for rapid change. The hard part is that the largest consequences live in the tails. Missing one rare transition can matter more than being slightly wrong on many ordinary days. To understand that tail, start with the engine. A hurricane is not powered by high wind. The wind is an output and an accelerator. The primary energy enters at the ocean's surface, where warm water and relatively cool, moist air exchange heat and water vapor across an area far larger than the eye. Sunlight warms the tropical ocean, but a storm does not ingest sunlight directly. Air moving across the sea collects sensible heat, and more importantly, water vapor through evaporation. Near the center, converging surface winds carry that moist air inward. Friction slows the air, but the pressure gradient keeps pulling it toward the core. As the air spirals inward, evaporation increases when the wind strengthens, because faster flow renews the layer of air touching the water. More wind can therefore produce more heat flux from the surface. That is the first positive link. Wind helps the storm extract the energy that can support still more wind. The moist air rises in deep thunderstorms. As water vapor condenses, latent heat is released into the air column. That warming makes the center of the storm warmer than its surroundings. A warm core expands the column, lowers surface pressure beneath it, and increases the pressure difference that drives air inward. The engine also needs an exhaust. Air that rises in the eye wall must spread outward near the top of the troposphere. If upper-level flow removes that air cleanly, mass can continue leaving the column while more moist air enters below. If outflow is blocked or badly asymmetric, the engine cannot process energy as efficiently. Now connect the pieces. Lower pressure accelerates inflow. Faster inflow increases surface exchange. Stronger thunderstorms release more heat. A warmer core lowers pressure again. This is not unlimited growth. ocean cooling, dry air, shear, eye wall changes, and land can break the loop. But while it closes, intensification can accelerate. That is why one sea surface temperature cannot predict the result. The storm needs a complete circuit from ocean flux to rising convection, upper level outflow, falling pressure, and stronger surface wind. Rapid intensification begins to make sense when we stop treating those as separate ingredients and watch the circuit assemble. Weather maps often highlight sea surface temperature, and warm water is necessary. But the skin of the ocean is only the top of a three-dimensional reservoir. A storm's wind churns that surface. If cooler water lies just below, mixing can pull it upward and cut the heat supply, even while the map began with an impressive surface value. Imagine two patches of ocean with the same temperature at the surface. Beneath the first, the warm layer is thin. Beneath the second, warm water extends much deeper. The storm may see the same number before arrival, then create very different water beneath itself after hours of wind-driven mixing. This is why researchers track upper ocean heat content and the depth of warm isotherms, not just the surface. Heat content asks how much warm water is available through depth. A deep reservoir can keep feeding turbulent exchange after the storm has stirred the top tens of meters. Ocean features such as warm eddies and the loop current can concentrate that reservoir. NOAA studies have shown that hurricanes crossing high heat content water can intensify when the atmosphere is also favorable. But the ocean does not force every storm to strengthen. Strong shear or dry air can dominate the response. The mechanism is a race. Wind extracts heat from above, while also mixing the water below. In a shallow warm layer, the storm uncovers its own break. In a deep warm layer, the storm can keep stirring without reaching enough cold water to shut the flux down. So the decisive visual is not a hot surface. It is a vertical slice. One ocean collapses into a cold wake as the mixing depth grows. The other keeps a warm column beneath the same storm. The difference is hidden from a flat temperature map, yet it changes how long the feedback loop can stay supplied. A hurricane does not passively float over its fuel. Its stress on the sea creates waves, currents, turbulence, and upwelling. The strongest mixing often follows the storm's moving wind field, leaving a cooler wake. This cooling is a negative feedback generated by the storm itself. If the storm moves slowly, the same patch of water can be churned for longer. That can expose cooler water and weaken the surface flux. But slow motion does not guarantee weakening, because the result depends on heat depth, current structure, salinity, storm size, and how quickly the mixed layer responds. Salinity can change the test. A fresh layer near the surface can sit above saltier water and create a strong density boundary. This barrier layer may reduce the storm's ability to mix cold water upward. The surface can therefore remain warm, even while powerful winds are trying to cool it. Now the ocean feedback splits into two paths. Along one, wind stirs cold water upward, heat flux falls, convection weakens, and intensification slows. Along the other, deep heat or strong stratification resists cooling, surface exchange persists, and the storm keeps receiving energy while its core organizes. This is one reason nearby storms can behave differently over water that looks similar from space. The important state includes temperature and salinity through depth, not just color at the top. Gliders, floats, sail drones, buoys, and expendable probes help reveal that hidden column. The storm is effectively performing an experiment on the ocean as it moves. Its wind mixes the reservoir, and the reservoir answers. A sharp cold wake is resistance. A surface that stays warm under intense mixing is permission. Rapid growth becomes more likely when that permission coincides with an open atmospheric window. Warm water cannot build a hurricane core through a dry middle atmosphere by itself. Deep convection entrains surrounding air. If that air is moist, rising clouds can remain buoyant and organized. If it is dry, evaporation cools the cloud edges, downdrafts strengthen, and the inner circulation can be disrupted. The location of the dry air matters as much as its average amount. A moist envelope around the center can protect the core even when drier air exists farther away. A dry intrusion reaching the inflow or eye wall can punch gaps into the convective ring and make heating lopsided. Vertical wind shear is the change in wind speed or direction with height. Strong shear can tilt the vortex, push thunderstorms away from the low-level center, and ventilate heat from the core. Low shear makes vertical alignment easier, but a low shear number alone does not guarantee organization. The most uncertain environments are not always the clearly good or clearly bad ones. Recent NOAA work emphasizes that moderate moisture and moderate shear can produce divergent outcomes. Small differences in inner core structure or initial moisture can decide whether the storm repairs itself or remains disorganized. Think of the atmosphere as a time-limited opening. Moisture can increase, shear can relax, an upper-level trough can move away. The storm must organize while that window overlaps deep ocean heat and before another hostile feature arrives. Forecasting the ingredients is not identical to forecasting their overlap. This is the first threshold in the full system. Deep heat supplies the engine, but moisture and shear decide whether the energy can remain concentrated near the center. When the vortex stacks vertically and dry air is excluded, the inner core can begin converting a favorable environment into a much faster rate of change. Inside a developing storm, thunderstorms do not begin as a perfect ring. Convective bursts flare in different quadrants, collapse, and reform. Each burst heats a column and moves air. The question is whether those bursts repeatedly occur close enough to the circulation center to strengthen one shared vortex. If the strongest convection stays displaced, it can spin up small local circulations without efficiently tightening the main core. When bursts rotate around the center and become more symmetric, their heating contracts the wind field and concentrates angular momentum. The storm starts to act like one machine instead of a collection of storms. Microwave satellites and airborne radar can reveal organization hidden beneath the cloud canopy. Forecasters watch for curved bands wrapping inward, a closing eye wall, a clearing eye, and stronger winds becoming more evenly distributed around the center. These are not decorations. They are signs that the energy conversion is becoming coherent. Vertical alignment matters here. The low-level circulation, mid-level center, and upper-level warm core need to overlap closely enough for rising heat to reinforce the pressure minimum below. Shear can separate those layers. Persistent convection can also help a storm resist shear and pull its structure back into alignment. Once the core closes, surface inflow encounters a stronger pressure gradient, spirals inward faster, and feeds a more continuous eye wall. Heating becomes concentrated where it most effectively lowers central pressure. Stronger wind then extracts more ocean heat. The feedback loop that existed on paper begins operating inside a real geometry. This is the structural payoff. Scattered bursts become a ring, the tilted centers stack, and the ring contracts around a shared eye. Nothing external had to flip a switch. The storm rearranged itself until each new pulse reinforced the same center. Organization turned available energy into accelerating wind. Begin anywhere on the loop. Suppose the pressure falls slightly. The pressure gradient strengthens, so near-surface wind increases. Faster wind increases evaporation and sensible heat exchange from the ocean. More moist energy enters the boundary layer and is carried toward the eye wall. In the eye wall, that air rises, condenses, and releases heat. The warm core strengthens. The air column expands aloft, and surface pressure falls further. Upper-level outflow removes rising mass. The new pressure gradient then supports still faster inflow and another round of stronger surface flux. Positive feedback does not mean energy appears from nowhere. It means an output strengthens the process that produces it. The energy still comes from the ocean, and the circulation still loses energy through friction and radiation. Rapid intensification occurs when the reinforcing links temporarily outrun the brakes. The radius of maximum wind can contract as the core organizes. The same angular momentum becomes concentrated closer to the center, and the pressure gradient steepens across a smaller distance. That can produce a rapid increase in peak wind even while the storm's total size changes more slowly. Now time changes character. Early improvements may be gradual because the core is incomplete. After alignment and closure, each increment of wind raises the flux available for the next increment. The curve bends upward. A forecast based on a slower recent trend can age quickly when the feedback loop becomes more efficient. But the loop is fragile. Cold water can reduce flux. Dry air can weaken convection. Shear can tilt the core. Land can remove the ocean supply. An eye wall replacement can spread the wind field and temporarily reduce the peak. Intensification is a race between reinforcement and interruption. The phrase hidden threshold can be misleading if it suggests one universal number. There is no single sea temperature, pressure, or shear value that guarantees rapid intensification. The threshold belongs to the coupled state: ocean depth, moisture, shear, storm structure, size, motion, and distance from potential intensity. Still, coupled systems can change abruptly when the last missing connection appears. A moist envelope surrounds the core. Shear relaxes enough for the centers to stack. A convective ring closes. The storm crosses deep warm water. Any one change may be modest, but it can complete the loop. This creates multiple plausible futures from nearly the same starting point. In one model member, dry air reaches the center and the core remains open. In another, convection blocks the intrusion and closes the eye wall. The members then diverge because their feedback loops amplify different early details. Researchers therefore find more than one pathway into rapid intensification. Some storms begin symmetric, others reorganize under moderate shear, some rely on exceptionally deep heat. Others intensify over ordinary warm water because the atmospheric and inner core conditions are unusually efficient. The label describes the outcome, not one recipe. That is also why hindsight can feel cleaner than real time. Afterward, we can draw the warm eddy, moist air, relaxing shear, and closing core as one chain. Beforehand, each link has measurement error and timing uncertainty. The exact moment of closure may occur between observations or below a satellite's opaque cloud shield. The suddenness is real, but it is structural rather than supernatural. A storm can spend hours assembling a network that looks inefficient, then cross into a state where heat, wind, convection, and pressure reinforce one another. The visible explosion is the late stage of an organization process already underway. Satellites provide the broadest continuous view. Visible and infrared imagery track cloud structure and temperature. Microwave instruments can see through upper clouds to reveal rain bands and eye wall organization. Scatterometers estimate surface winds over parts of the ocean. Yet each sensor samples a different layer, time and footprint. When aircraft reconnaissance is available, hurricane hunters fly through the circulation and measure flight level wind, pressure, temperature, and humidity. Instruments estimate surface wind below. Repeated passes locate the center and radius of maximum wind, showing whether the core is tightening faster than satellite estimates suggested. Dropsondes fall by parachute and report vertical profiles of pressure, temperature, humidity, and wind from aircraft altitude to the surface. They can sample the eye wall, inflow, and surrounding environment. Those profiles help distinguish a moist protected core from a storm still vulnerable to dry air or shear. Tail Doppler radar maps wind and precipitation through a three-dimensional slice of the storm. It can reveal vortex tilt, convective asymmetry, eye wall structure, and the location of the strongest winds. Sending these observations into forecast models improves the initial storm that the model is asked to evolve. The ocean requires its own observing network. Gliders, floats, buoys, sail drones, and probes deployed from aircraft measure temperature and salinity below the surface. NOAA notes that models using upper ocean observations can improve intensity forecasts because they represent the reservoir the storm will actually mix, not only the skin temperature. Combine the instruments and the storm becomes a volume. Satellite sees the canopy, radar sees the rotating core, dropsondes cut vertical profiles through the air, and gliders slice the ocean below. Rapid intensification is a three-dimensional problem, so the observing system must assemble a three-dimensional initial condition. Modern hurricane models solve the evolving atmosphere and, in coupled systems, the ocean beneath it. High-resolution nests follow the vortex, so clouds, rain bands, and eye wall gradients can be represented. But no model begins with complete measurements, and small initial differences can grow rapidly once feedback becomes strong. Inner core moisture is especially important. Research by Carrie Emanuel and Fuqing Zhang showed that errors in the initial moisture of the core can produce large intensity errors even when the starting maximum wind is correct. A model can know how fast the storm is now and still misread how ready it is to accelerate. Ensembles address that uncertainty by running many plausible versions of the storm and environment. Some members intensify rapidly, others do not. Statistical and dynamical guidance convert those outcomes and known predictors into probabilities for different wind increases over different time windows. A probability is not a countdown. 20% does not mean intensification begins 20% of the way through the day. It means similar information and model states produce that event in a fraction of plausible outcomes. As new observations arrive, the distribution can shift sharply. Forecasters combine model guidance with satellite trends, aircraft data, ocean conditions, and known model biases. They may raise the official intensity forecast before every deterministic model shows the same jump, or hold below an extreme member that lacks supporting structure. The forecast is expert synthesis under changing evidence, so the honest product is not one perfect curve. It is a fan of futures that narrows and moves as the storm is sampled. When the high-intensity branch gains support, the decision problem changes before certainty arrives. Waiting for the final observed category can spend the remaining preparation time. Rapid intensification begins with a reservoir, not a category. Warm water must extend deeply enough to survive mixing. Moist air and manageable shear must create an atmospheric opening. Convection must organize close to the center. The vortex must align, close, and concentrate its heating. When those pieces connect, wind increases surface flux, flux supports convection, convection strengthens the warm core, and lower pressure accelerates wind. The loop bends the intensity curve upward. When one piece breaks, the loop weakens and the curve flattens or reverses. That system view explains two storms over the same warm ocean and why they can diverge. It explains why a forecast may identify favorable conditions without knowing the exact transition hour. It explains why measuring the water below and the moisture inside matters as much as tracing the storm on a map. For people in the path, the practical lesson is not to predict the eye from a diagram. Use current National Hurricane Center and local emergency information. Intensity is only one hazard dimension, and dangerous surge, rain, tornadoes, and wind can extend far from the center and evolve on different schedules. The deeper lesson is about how systems surprise us. A dramatic outcome often looks sudden because we notice the final state change, not the quiet assembly of connections that made acceleration possible. Better forecasts come from observing those connections, representing their uncertainty, and updating decisions before the loop fully closes. A hurricane does not simply find warmer water and become stronger. The ocean, atmosphere, and vortex negotiate every increase. Rapid intensification is the moment that negotiation briefly becomes reinforcement. What changes fastest is not only the wind. It is the storm's ability to make its next increase easier than the last.